Hi, my name is Boyang Zhu, and I'm a third year undergraduate computer science engineering student. This summer, I work with Professor Wellman in the Strategic Reasoning Group, and today I'll be giving a short introduction to empirical game theoretic analysis. So here's an overview of some of the things that I'm going to be talking about. I'm going to start by giving the definition of a game. I'm going to give a couple simple examples of games just so that you become familiar with the idea. And then I'm going to talk about some of the research that we actually do in our lab, as well as some of the applications of this method. So before we talk about empirical game theoretic analysis, we need to talk a little about game theory itself. So what is game theory? Game theory is the study of games, and a game typically consists of three things: a set of players, a set of strategies, and payoffs. Players are essentially the agents in your game, and strategies are the actions that they can take within your game. Payoffs are the utilities of each player given some outcome of the game. And I'll make this more concrete when I give an example in the later section. So game theory is interesting because there are typically strategic interactions between players. So what this means is that your payoff depends not only on the action that you take, but also the action that your opponents take. And also, within games, there are typically probabilistic elements that make things a lot more interesting. Here's an example of a game that we're all familiar with: rock, paper, scissors. So as you can see, you have two players, player one, player two. Each have three strategies: rock, paper, scissors, and their payoffs are summarized in the payoff matrix. So for example, if player one plays rock and player two plays paper, paper beats rock, and player one gets a payoff of -1, and player two gets a payoff of +1. But despite their seeming simplicity, there are some problems with games that make them a difficult tool for researchers to use. So first of all, the complexity of games is exponential in the number of players and strategies. So in the previous example of rock, paper, scissors, if there were 3 players instead of 2, you would have 3 cubed, which is 27 entries in your payoff matrix instead of 9. So as you can see, the complexity increases very quickly. Second of all, there are many probabilistic elements that make the game difficult to analyze using traditional mathematical methods. Our solution to these problems is called Empirical Game Theoretic Analysis, or EGTA for short. EGTA is a simulation-based approach, and essentially what you're doing is filling out the payoff matrix of the game one cell at a time. So in the rock, paper, scissors example, we might start by assigning player 1 to play rock and player 2 to play scissors. We simulate the game, and we see that player 1 receives a payoff of 1, and player 2 receives a payoff of -1. And so we have now obtained a cell in our payoff matrix. Whenever our game has probabilistic elements, we sample the random variables in question from their distributions. So suppose we're in an auction scenario where my private valuation of the good is normally distributed with mean 0 and variance 1. For each simulation, we draw a value from this distribution. So for example, if on the first simulation I draw 0.2, then that becomes my private valuation for the duration of that simulation. But whenever we have probabilistic elements, a single sample holds low statistical power. As such, we need to sample the game multiple times and observe the asymptotic behavior by using traditional statistical methods. There are a few benefits of EGTA. First of all, and most importantly, it allows us to study games that are not solvable using traditional methods. Second, because we're filling out the payoff matrix one strategy combination at a time, it removes the need to fill out every entry of the payoff matrix. Third, EGTA uses existing statistical methods, so you don't need to develop a new theory to use this method. And fourth, EGTA can be easily automated. But despite these strengths, there are also a few weaknesses of the EGTA method. First of all, you need a large number of samples for your results to hold statistical power. This means you need to simulate the game multiple times, and this can get computationally expensive very quickly. Second, because the EGTA method is statistical in nature and depends on data, the accuracy of your results are not always guaranteed.
Finally, as we talked about before, there are a lot of complex strategic interactions between agents in games. And so a lot of times you can't make parametric assumptions about the properties of your games. So, for example, we might find that payoffs are not always normally distributed. So even though the EGTA method is very general, I just wanted to wrap up by giving a couple applications of the EGTA method from our lab. The first is a supply chain game where agents manage a supply chain and try to maximize their profit over the entire duration of the game. The second example is combinatorial auctions where players bid for multiple items simultaneously. The final example is latency arbitrage, where financial agents try to exploit arbitrage opportunities that arise from hardware latency effects. So, as you can see, all of these scenarios are fairly complex and cannot be analyzed using traditional mathematical methods. And that is the advantage that EGTA affords us.
Hi everyone, so that's my video. Just wanted to take this opportunity to say thank you to both Professor Wellman and all of the graduate students in our lab for a great summer of research. I hope you enjoyed my video, and thanks for watching.